CCI, Crash Course Instrumentation, presents Episode /66, KCL in plain English, share the node, cold open. At a T in a water pipe, whatever flows in must flow out. At a T in a circuit, a node, current does the same thing. Today you will learn to read the T and make Kirchhoff's current law feel obvious. Viewer promise. By the end, you will call current directions in plain English, read a node like a traffic cop, and check your work on the bench without any formulas. Tiny historical note. In the 19th century, Gustav Kirchhoff described how charge is conserved. At any node, the ins and outs balance. We still use this rule in every panel and on every bench. Section 1. The water T picture. Picture a pipe T, flow comes in, then splits. Or two flows merge and exit. Either way, the T does not make or destroy water. A circuit node works the same way. Current is moving charge. The node does not create or erase charge. Plain words only. Call currents that head into the node incoming. Call currents that head away from the node outgoing. When you total them, incoming equals outgoing. Section 2. How to read a node. Pick a single node to study. Put a sticker dot next to it on paper. Draw short arrows on each branch that touches that node. Do not worry if an arrow guess is wrong. It will sort itself out on the meter. Say each arrow out loud. Incoming or outgoing. The story at that node. The sum of incoming flows matches the sum of outgoing flows. If the story does not balance, you missed a branch or flipped an arrow midway. Section 3. Bench Mini Lab. Proof by clamp and DMM. Build a simple parallel test. A low-voltage supply feeding 2 or 3 resistive branches. Keep it safe and neat. Close the switch so current flows. Mark one shared junction as your node of interest. Method 1, series meter. Lift a branch, insert the DMM as an ammeter, and read that branch's current. Speak incoming or outgoing for the way it meets the node. Method 2, DC clamp meter, if you have one. Clamp each branch wire and note the sign. Speak the direction at the node. Now, add up your spoken incoming branch values and your spoken outgoing branch values. They should balance. If not, check for a missed return path or a wiring mistake. Pro tip: if your meter shows a negative current, your arrow guess was opposite the actual flow. Keep your arrow list, keep going, and say the direction that meets the node. Section 4. Common pitfalls and fixes. Pitfall: forgetting a branch that hides in the return path. Fix: trace the whole loop with your finger and count every wire that touches the node. Pitfall: changing an arrow mid-test. Fix: circle the node and draw arrows once. Do not edit them during measurement. Pitfall: mixing series and node logic. Fix: remember, same current everywhere applies to one path. Node balance applies where paths split or merge. Pitfall: relying on color alone. Fix: confirm which conductor actually meets the node. Do not trust insulation color. Section 5. Field checklist you can use today. Choose one node to analyze. Draw arrows for every branch that touches it. Say incoming or outgoing for each branch. Measure branch currents one at a time. Confirm incoming equals outgoing. If not, find the missing branch or fix the arrow. Section 6. Real-world snapshots. 3-wire power. The center neutral node balances house loads that share a supply. When loads are even, the neutral current drops. When they are uneven, the neutral carries the difference. Same node story. Same. Panel troubleshooting. A feeder splits to drives and lights. Read the node at the split. The sum that leaves must match the sum that arrives. 420 MA loops. In a series loop, the same current passes everywhere. But at junctions in monitoring gear, the node still balances ins and outs. Quick self-check. You measure 2 branch currents into a node and 1 branch current out. Your totals do not match. What should you check first? Answer key: a missing branch, a wrong arrow, or a wiring mistake that bypasses your meter. Tease for the next episode. Next up, current dividers. We will show how parallel paths split flow in everyday gear with no formulas, only arrows, meters, and clear language. Call to action. If this helped you see KCL, please like and subscribe so more students and techs can find it. Credits: on-screen and spoken. Thank you to Tony Capult and the open source community for the model materials that make Crash Course Instrumentation possible.